This is the last problem of tutorial 2, problem number 10. A load is supported as shown in the figure P. The question is, what angle theta will result in the least weight design if both members are stressed to yield Y? Plot the normalized weight of the structure versus theta. Now, if you look at this particular configuration, let's first solve for normalized weight with respect to theta. Okay, so let's take the angle to be theta and then solve this problem first. Okay, if you look at this problem, this is a very simple problem. Both of them are going to extend so that we're going to get something like this. The extension of AB will be the extension of BC also. So delta of AB is equal to delta of BC. We also use equilibrium at B in order to be able to find out these two forces. By symmetry, FAB is equal to FBC, so that I can write this as FAB here and FAB here, from which it is possible for me to find out what is FAB. The first exercise. Now, if it has to be stress to yield, this should go to Fy. Okay. Remember, this will be in terms of P, so we can find out this as a function of Py. Let's say this is what we are going to do. Okay. Please remember, by solving the equilibrium, this will be a function of P and theta, and therefore we will get Fy as a function of theta and Py. Mind you, if the angle is this theta, this is theta prime. If this theta prime is very small, we'll get FAB to be closer to P. If this angle is very large, we'll get FAB to be much greater than P. Okay, but if the angle is very small, the length becomes very, very high, because we have L by 2 as the horizontal length, and if this were, let's say, theta prime, then we can find this to be L by 2 into 1 by sine theta, to be the small l, total length of this. As theta becomes smaller and smaller, this length goes up. So L goes up as theta prime comes down. Okay, so we have this scenario, but the force also comes down. But if FAB is to be greater, then the length will come down. Therefore, we have the other scenario where FAB in fact goes up as theta prime goes up. So we have this trade-off that we see here. So we write down these equations and we optimize for the length L, so that we find out what would be dl by d theta or d theta prime is equal to 0. And this will be the optimized design. Okay. We use this condition in order to get the relationship between the P and Fy. That's how we solve this problem. It's a very simple problem. Once we do this, we will have a function in terms of theta. If you draw that, you will find that at a particular theta, and I'm guessing it is 45 degrees, we will get some curve which seems to give weight versus theta to be something like this, so that this weight is the minimum that we find. Try it out in this way.